Good evening, everyone. I am Asmata Basu, a PhD candidate at the Oklahoma State University. In this session of Modeling and Simulation of Aircraft, UAS, UM System Dynamics and Environments, I am going to present some of our preliminary work on design of wind-hour SUS simulation pipeline for urban air mobility. Urban air mobility, or UAM, envisioned for a safe and efficient aviation transportation ecosystem for low-altitude urban airspace. Studies have found, despite potential to revolutionize package delivery, emergency response, passenger mobility, UAM suffers from different challenges, such as environmental condition, safety and certification, social acceptance, etc. Academic researchers as well as the commercial facts are showing how the small unmanned aircraft system operation being affected by the inclement weather. A survey between 1,700 people shows that around 52% of respondents expressed increased level of fear and concern while flying in the turbulent wind. UPS flight carrier that obtained a air carrier certification from Federal Aviation Administration back in 2019 recently says that wind and rain are holding back their delivery times. In a multidisciplinary research group at the Oklahoma State University, we are working towards safe wind-hour navigation for small unmanned aircraft systems in a low-altitude operation. Our focus was to do a realistic wind simulation, increase wind situational awareness, and develop high-fidelity simulator. To do this, we start with a research group study with subject matter expert. With the subject matter expert, we identify and derive the specific design principles. Design a simulation pipeline for wind-hour SUS operation for UAM. We then choose and utilize open source code base for the extension to be used by the community. Our subject matter experts were 4 pilots, and 3 of them have Part 107 certification. The group study was conducted as a semi-structured interview with open-ended question answer. We asked the subject matter expert regarding their inclination toward flying in windy situation. The current user interface's ability to provide weather information. We also talked about wind-adjusted autonomous controller feature and wind-hour trajectory management features. During the interview, we noticed pilots' disinclination toward flying in the windy weather. We also recognize the pilot are inclined towards more information, such as information to increase the situational awareness our windy condition, the wind-hour trajectory management or wind-corrected trajectory management feature, as well as trusted autonomous controller feature. So how can we better support operation in the wind? We can design to wind-hour user interface with information components recognized in the study. We do a pilot in the loop flight simulation in the simulator that mimic the realistic environmental effect. Also test and evaluate the effect of increased situational awareness. However, the challenge was there is no open source simulator that has spatial temporal wind simulation capability. The current user interface usually doesn't provide the wind's velocity information, and limited simulator available for the small unmanned aircraft system pilot train and test flying in the urban scenarios. In the case of crewed aircraft, it is common for the simulator to come as integrated with the control station. However, this is not the case for the small unmanned aircraft system. So in this case, we choose two different code bases, such as AirSim and Ground Control Station, and their compatible communication protocol for the simulation. We extend the current UI to wind-hour supervisory UI for our work. We also integrate space and time-varying atmospheric boundary layer wind profiles into the AirSim and construct environment that resembles the urban cluttered airspace. We utilize the SITL capability of AirSim with Ground Control to PX4. Mavlin API is used for the communication between AirSim, PX4, and the Ground Control Station. The block diagram shows the integrated architecture of the simulator. In the AirSim, we integrated the wind safety data through the wind module that we developed. We also developed wind velocity widget, optimal trajectory display widget, and wind buffer widget into the Ground Control Station. Existing AirSim has the capability to simulate static wind. It treats wind as a constant global velocity that can be changed only at startup. In the extension, we incorporate wind dataset from a high-fidelity large area simulation from our collaborator. Large area simulation is capable of modeling atmospheric boundary layer more accurately than the other wind models such as Dryden and Bokerman model. To integrate this data, we develop wind module object into the AirSim core physics engine. This object loads and handles the wind data. With that, instead of a global velocity, local velocity is computed dependent on the vehicle position within the wind grid. We also generate scenarios that resembles urban area. In the example, drone is simulated in the OSU campus. The drone is controlled through a PS3 controller. The scenario is generated in multiple steps. We first utilize the OpenStreetMap freely available spatial data. However, the spatial data needs additional cleanup before it can be imported to the Unreal Engine. We use open source graphics tools at Blender for the cleanup and Unreal DataSmith plugin to import the scenario into the Unreal. Next, we extend Qground Control Station or QGC. QGC is built in Qt and it is extensible using C++, QML, and JavaScript. We developed wind widgets to display the wind velocity and wind arrow mission planner to facilitate the wind arrow trajectory management features. The first feature we incorporate into the QGC was wind velocity widgets. We include 3 different display designs for the pilot to choose from. 2 of them are compass style and the other one is gradient compass style. In the first compass style display, the magnitudes are shown component-wise. The plan and direction is represented in the compass. The vertical direction is represented as a downward or upward arrow. In the second compass style display, both the plan and direction and magnitudes are split into north and east component. The vertical direction remains the same. The gradient and compass style display shows 2 color bars where the blue line changes its position based on the strength of the wind. The planar direction is shown in the compass. The vertical direction, the blue line goes up or down based on the direction of the wind. Based on our SNS preference during our research with the study, we introduce a buffer wrapping around the waypoint trajectory. The buffers are expected to provide the pilot with a visual reference. The inner margin provides a visual reference for the pilot to stake, and the outer margin provides the pilot a reference to an unexpected deviation. Another feature of our trajectory management was alternate path suggestion. It should be noted that this is a placeholder algorithm for a future implementation of wind optimal trajectory suggestion. Current implementation disregard intermediate points to reach a final destination. After pilot chooses some waypoints to reach a final destination, QGC shows the alternate path and prompt a question whether pilot wants to accept or deny the new trajectory suggestion. If the pilot accepts the suggestion, the trajectory is then updated. Our future work involved feature updating the QGC and the pilot in the loop simulation. We'll be updating a wind optimal trajectory design in the QGC and also include safety and risk margin analysis. For the pilot in the loop simulation, we'll be testing the user experience with the wind arrow QGC and also design mission and experiment for the pilot evaluation of our wind arrow simulation. Would like to thank NSF for funding our study and thank you for listening to my presentation.